Hi everyone, greetings to all of you. Now in this video, I will show you how to use the energy level method in Born Haber Cycle. Now previously in your previous class, I had shown you how to construct energy cycle for Born Haber. Basically, we have enthalpy of formation, enthalpy of atomization, ionization energy, electron affinity, and lattice energy, which is, in short, we say it as FAIEL. Like I said in the previous class, I show you how to construct energy cycle. In this video, I'm going to show you how to construct Born Haber in energy level method. Now, I'm taking the same example as in your lecture notes. Okay, so how are we going to construct energy level? Now, to construct energy level, first you have to draw the y-axis and label it as enthalpy. Next, draw the x-axis but without the head of the arrow. Now, let's write the ionic solid. In this question, the ionic solid involved is potassium chloride. Therefore, write the potassium chloride here. Do not forget to write the stat as well. Okay, so it is the same thing as in energy cycle. So we are going to start with enthalpy of formation first. So for enthalpy of formation, which is this one. So let's see. Write like this. Okay, put the equation of the formation. Now, as you can see, the enthalpy here is negative. Okay, it is negative. So if the enthalpy is negative, you have to draw an arrow going down. An arrow going down represents heat release. So we going to draw it like this. Put the enthalpy there. Okay. Okay, we are done with formation. Now let's go for atomization. So I will start with the enthalpy of atomization for potassium. Now enthalpy of atomization for potassium is the first equation here, and it is positive. So how are we going to draw it? Okay, you have to draw a line and the arrow must be going up. Arrow going up means it is absorbing heat. So write down your equation here. Now let's take a look. As you can see at this equation, at this equation that we draw, the only changes that you can see is for the potassium, where the potassium change from solid to gas. Change from solid to gas. However, the chlorine gas remain unchanged. Therefore, this means this is involving enthalpy of atomization for potassium only. So don't forget to write down the enthalpy. Okay, before we go further, as you can see, I draw a different length here. Okay, this one has big length or big gap, whereas for enthalpy of atomization for potassium, I draw it with a small gap. So this small gap is actually drawn, or it's actually drew when according to the value of the enthalpy. Now the value of the enthalpy here is 436. So it is actually bigger than the enthalpy of atomization, which is 90. So that is why for enthalpy of formation, I draw a big gap, which shows the enthalpy is bigger. And For enthalpy of atomization, I draw with just a small gap like this, which means the enthalpy involved is just a small enthalpy. Okay? So you have to draw it like this. Okay. So let's proceed with the third one, which is enthalpy of atomization for chlorine. So enthalpy of atomization for chlorine is in the third equation. So let's see. Now, it involves 121 kilojoule per mole, and it is absorbing heat. So we are going to draw it like this. Now, if you look here, the potassium gas is not changing, and only the chlorine change from chlorine gas or chlorine molecule to gaseous atom. Okay, you can see here, it is changing here. All right, which means this involves enthalpy of atomization. Therefore, we write it like this. So now you compare the length or the gap. Okay, the gap of enthalpy of atomization for potassium is smaller compared to enthalpy of atomization for chlorine. But still, the gap for enthalpy of formation is bigger compared to the other two. Okay, so we are done with formation, we are done with atomization. Now let's proceed with ionization energy. Okay, so for ionization energy, we took the second equation. And if you look at the second equation, it involves 418 kilojoule per mole. So can you guess the gap of your level? Yeah, it should be bigger. Okay, so we make it bigger but smaller than the formation because it involves only 418 kilojoule. So we are going to draw the arrow up since the enthalpy is positive. And as you can see, the potassium gas changed to potassium ion. So here we go. But the chlorine is still remain unchanged, the chlorine gas. Okay, so we are done with ionization energy. Now let's proceed to electron affinity, where we are going to change the gaseous atom of chlorine to ion. However, if you look here at the fourth equation, okay, here at the fourth equation, the enthalpy involved is negative. So how are we going to draw it going down? How are we going to draw the arrow going down? Okay, so this is the tips. What you do, you lengthen the line for this, and then make another line here. Should be smaller than 418 because it involves 364. Put it going down, which means from this equation, which is the chlorine gas, will change to chlorine, or it change to chloride ion. And because it is heat, it releases heat, then the arrow should go down. And don't forget to put the enthalpy negative 364. Now, lastly, we have to find the lattice energy. Now, for lattice energy, we must have gaseous ion. So we do have it here, gaseous ion. So this gaseous ion will produce the ionic solid. So just directly put it down. But we don't know what is the lattice energy, so we put it like this. Okay, so there you go. This is your energy level. You have to do it one by one, level by level, and different gap of level. And the different gap to each level is corresponding to the value of the enthalpy. The bigger the value of the enthalpy, the bigger the gap. Okay, now let's proceed with the solution. So for the solution, okay, it is SM, which is enthalpy of formation, equivalence to all the enthalpy that you have here. Now, I give you 2 minutes to calculate it. You can pause this video first. Okay then, have you done your calculation? So let's take a look at the answer. So the answer that you should get is negative 701 kilojoule per mole. Okay? So that is the first example for Born Haber energy level. Okay, now let's take a look at this example. So this question gives you five types of enthalpy. We have enthalpy of formation for sodium chloride. We have enthalpy of sublimation for sodium. We have first ionization energy for sodium, enthalpy of atomization of chlorine, and also electron affinity of chlorine. Now, before we go to the solution, let's take a look first. Perhaps you might wonder, what enthalpy is this? So, enthalpy of sublimation. Now, if we write the equation, okay, we see sublimation. Okay, sublimation means it is a process from solid to gas, which means from sodium solid, it will change to sodium gas. Okay, and this is what we call sublimation. So the enthalpy should be positive 10 at, okay, 10 at. However, okay, as you can see, this process also produces what we call as gaseous atom. Okay, it is also producing gaseous atom, which also we can see it's almost the same, like, or it is almost the same, but fulfilling the definition of enthalpy of atomization. So what we can say here, the enthalpy of sublimation for sodium is equivalent to enthalpy of atomization for sodium. Okay, all right. Now that is the first thing. Second thing, I will always look at the value first. Okay, I will always look at the value. So as you can see, the biggest value is 500. So we know, okay, so this 500 must be having the biggest gap ever. And then the smallest one is 10 which is the enthalpy of sublimation for sodium. So it is good for us to take a look first at all the value so that we can we can predict the gap of each level. Okay, we can predict the gap of each level. So this question asks you to construct the Born Haber cycle and determine the lattice energy. So let's go. Okay, so let's take a look at the solution. As usual, start with the y-axis and don't forget to put the label enthalpy. And then next, the x-axis. Third one, write down the ionic solid. So in this case, our ionic solid is sodium chloride. Okay, so let's start with enthalpy of formation for sodium chloride. Now, in this question, it does not give you the equation. So you have to know how to construct the equation by yourself. Now let's take a look, like sodium chloride. We know when it comes to enthalpy of formation, the sodium chloride must be constructed from its own element. Okay, it must be formed from its own element. So its own element, which means sodium solid and also from chlorine gas. Now since our chlorine here is 1 mole, therefore here also you have to put half mole. Don't forget that. Okay, next one, enthalpy of formation here is releasing energy. So we have to draw it. We have to draw the arrow going down. And do not forget to put the enthalpy -411 kilojoule. Okay? Now we are done with enthalpy of formation. So let's take a look at the next one. Atomization. So I would like to start with sublimation of sodium, or the atomization of sodium. So it is 108 and it is positive. It should be smaller the gap should be smaller compared to the gap for formation. We are going to write it like this. Okay, so as you can see, the changes only happen at sodium, where the sodium solid changed to sodium gas. So don't forget to put your enthalpy here, okay? Now next one, enthalpy of atomization for chlorine. Okay, it is a the enthalpy is slightly bigger compared to the atomizations of sodium. So we can draw the gap slightly bigger as well. Okay, put it like this because it is a positive. It is absorbing heat, and we got it like this. So don't forget to put the enthalpy here. Okay. So we are done with formation and also atomization. Now let's proceed with ionization energy. So ionization energy for sodium is 500. Okay, so we have to draw the gap bigger. Okay, so I draw it like this. All right. So what is the changes? Okay, as you can see, the sodium will change to sodium ion and the chlorine will remain unchanged. Okay, so we have this one, we have this one. Done with ionization energy. Let's proceed with electron affinity. Okay, electron affinity. So electron affinity is negative. It should be going down. So whenever you see it going down, okay, just lengthen your line. Do it something like this. Okay. Anggarkan, okay, it's around 364. It shouldn't be bigger than the 500. So going down and write your equation here. So as you can see, the changes is from the gaseous chlorine to the chloride gaseous ion. So you get this. And lastly, for your lattice energy, got this. So let's take a look at the solution. Okay, so it is the same enthalpy of formation equivalence to all the enthalpy. And if you calculate, you're going to get -776 kilojoule per mole. Did you get it? So here in this slide, I attach together with the one that I draw on a paper. So you can see it's quite different also. Okay, you can see the symbol I put here also negative delta H. Yes, it is acceptable. And then all the arrow is in one line, also acceptable like that. But I want you to focus on the gap. Okay, the gap is totally they are having the different gap in each level. So please take note on this. Okay. Okay, now let's take a look at these questions. this question is slightly different from the other two questions because it involves second ionization energy. So what I meant is, okay, we have here copper oxide, which should be CuO. As you can see here, we have second ionization energy. And for oxygen also, we have second ionization energy. So usually in my previous example, we have only one ionization energy and one electron affinity. So whenever you get something like this, what you should do, all right? So as usual again, identify which enthalpy gives the biggest value. So as you can see, it is second ionization energy. We have here 1960. And then take a look and try to get the idea of which enthalpy will get bigger gaps. Okay, you want to do it? Maybe you can try it. You can pause these questions first, and then you can see the solution in the next slide. Okay, so let's take a look at the solution. Okay, don't forget to draw the axis and then identify the ionic solid. So in this case, we have copper oxide. And let's start with formation. Okay. To form this, we need copper, which is in solid state, and also half moles of oxygen gas. Since it is releasing energy, then we draw it like this. Okay, next one, as usual, I will start with enthalpy of atomization for copper. So it is absorbing heat, and there you go. This is the changes. Copper solid change to copper gas. And enthalpy involved is positive 339. Next one, we continue with enthalpy of atomization for oxygen. Still, it is absorbing heat. And there you go. The half mole of oxygen gas change into oxygen gaseous atom. And the enthalpy involved is positive 248. Slightly lower compared to atomization of copper. Next one. We start with the first ionization energy for copper. We get this, positive 745. And I will directly continue with the second ionization energy for copper ion, which is this. Okay, there you go. Now, if you look at the ionization energy, we have done with ionization energy of copper. So this is the first, this is the first IE. Okay, guys, and this is the second IE, right? Okay, so let's proceed with electron affinity. As you can see in the questions, the first electron affinity is releasing heat. So we have to draw the arrow going down. As usual, lengthen it and put it like this, which is negative 141. Okay. Now, if you look at the data for second electron affinity, you can see that it is positive, which is going up. So how are we going to draw the energy level going up? Don't worry. Again, you lengthen it. Make sure it is going up. Put another line and put the equation. Okay, so as you can see, the changes is from O minus negative gas to O2 minus, or it become oxide ion. Okay. Right. Now, we don't forget to put the enthalpy here, 791. So for lattice energy, where should we put the arrow going down? Is from here. Because we know to produce CuO solid, if you want to produce copper oxide, okay, you have to get copper ion and oxide ion. So what is the lattice energy? Calculate, and let's see the solution at the next slide. So as usual, everything is equivalent to the enthalpy of formation. Okay, though as you can see here we have IE only one, but actually this one represent both IE1 and IE2, as well as this one also, both EA1 and EA2. So calculate it and you're going to get negative 4097 kilojoule per mole. Okay. Okay, so let's take a look at the last equation. So in this questions, we are going to construct the Born Haber cycle for the formation of magnesium fluoride. So magnesium fluoride is MgF2. Okay, MgF2. So how are we going to construct it? Let's go. Okay. Let's see. As usual, don't forget your axis and don't forget to write your ionic solid, which is MgF2 here. So we always start with formation. So we have delta H equivalents to negative 1124 kilojoule. Arrow going down because it is heat release. Start with atomization of magnesium. So we are going to get magnesium gas. The enthalpy is positive 148 kilojoule. Next, we have to start with the enthalpy of atomization for fluorine. So from fluorine, it will become 2 moles of gaseous atom for fluorine. Okay, so now in the question, you are given enthalpy of atomization, which is equivalent to positive 159 kilojoule. But please remember one thing. The value given to you here is only for the production of 1 mole fluorine. Okay, 1 mole fluorine gas. Because if you read back the definition of enthalpy of atomization, it is referring to the production of 1 mole of gaseous atom, right? Okay. However, if you look here, you have 2 moles of fluorine gaseous atom. Okay, you have 2 moles. But the value given to you here is 1 mole. So what you have to do? You have to times the value to 2. Because at this time, you are producing 2 moles of fluorine gaseous atom. Okay? Now next, we have done with formation, we have done with atomization. Now let's go to ionization energy. So the first IE for magnesium, which is to produce Mg+, it involves positive 738 kilojoule. And then I will go to the second ionization energy for magnesium to produce Mg2+. It involves 1450 kilojoule. Next ones, okay, we start with EA. Okay, we have done with both IE. We proceed with EA. It is releasing heat, so we have to draw it down here like this. And we got this. However, again, the enthalpy or the electron affinity value given here is for 1 mole only. Okay, this one is for 1 mole formation of 1 mole of fluoride. But we have 2 moles of fluoride here. Therefore, don't forget to times this value with 2. And finally, we want to find the lattice. We already have all the gaseous ion here. Can going down, can find lattice energy. Okay, we know that Mg2 plus 2 fluoride ion will produce MgF2, which is this one. Okay, so how are we going to calculate the lattice energy? Okay, so as usual, enthalpy of formation is equivalent to all the enthalpies in the reaction given to you, and you should get negative 3112 kilojoule per mole. So here is your homework. Don't forget to do it. Thank you, everyone.